So here we are talking about melt water and heat waves. You already know that this is all about how global warming and climate change are actually impacting everything on Earth, right? So we talked already a few things. We'll talk a few more, talked about a few things, and we'll talk about a few more things in this podcast. We will talk about melting poles. In fact, it's not just the poles, actually, even the glaciers in the mountains in low latitudes like the Himalayas are melting, and Venezuela is right now waiting desperately to see if its glacier will completely disappear, which would be the first glacier to completely disappear since the Industrial Revolution. That's not good news, right? Whether we want to agree about human role in doing this, whether we are responsible or not, whether it's natural or not, it's always not, sad to see a nice glacier disappear, even though it may be part of the natural cycle in some time during the past history of the earth. Right now, the risk that we are doing something, it has to be considered, right? So let's read a bit about this. In Greenland, you can hear climate changing. What does it mean? There are glaciers that are melting and they are flowing as water, like waterfall. Sometimes it's just a drip, drip, drip of the glacier drops, melting water falling down. This is the sound of melting ice. The crackling sounds can also be heard sometimes. Walk on a bit and Greenland and you won't hear any more dripping. It'll be drowned out by the rushing river that is carrying away the melt water. So it's not just a drip drip, it soon adds up to a river with huge force. They carve bright blue path through the ice because ice crystals are so clean. They tend to scatter light and create these beautiful colors. I'll show you a picture at the end of this podcast. Closer to the sea, you can hear the squeaking and the creaking of the sheets of ice. They break away from the glaciers and float quietly out into the oceans where they slowly melt. Remember, the Titanic hit one of these pieces of glaciers that floated down into the North Atlantic in the path of the Titanic, and during that time it wasn't yet global warming. There are natural calving, calving, calving processes which can break off the glaciers. Now the question is, how are we accelerating these things, right? You can find glaciers wherever snow falls on land and it's cold enough for the snow to survive the summer so that it doesn't melt, and more snow falls next year. So that's around the North Pole and the South Pole, and also in some mountains like the Himalayas and the Andes and the Alps, but also in other places, mainly in the mountains, because it can be cold enough there too as you go high in altitude. Maybe you have skied on a glacier snow. Perhaps you have seen the photos of giraffes and elephants with snowy Mount Kilimanjaro in the background, in the middle of Africa. Even there, not far from the equator, you can find glaciers, because if you go high in the altitude, temperatures are colder and snow can stay year after year. But for how much longer? All over the world, glaciers are shrinking. In Switzerland, Argentina, Tanzania, Nepal, Venezuela, this will have serious consequences if you melt so many glaciers. Of course, sea level rises because the glacier meltwater ultimately flows into the ocean, but now you are an expert. The albedo feedback, as you melt the glacier, the reflectivity albedo goes down, which means less sunlight is being reflected, which means you are keeping more of it, which means you are going to accelerate the warming, right? So we have to worry about these things. Billions of people use glaciers as a water supply. In the natural world, the mountain glaciers in Himalaya melt every year and provide water into the rivers that people depend on, the Indus River, the Ganga River, and so on and so forth, and many other rivers across the world. Mekong, whatever, many rivers get glacier meltwater during some season. And in natural variability also, it happened before global warming became, climate change became so dominant. So people are used to this water cycle of glacier building, providing meltwater, building meltwater. So there was an equilibrium. There is an equilibrium line where the glacier grows and the glacier melts. The largest ice packs are in Antarctica and Greenland. They have been there since the beginning of the ice ages, millions of years ago. You can estimate how long ago that Greenland began to build a glacier and how long ago that Antarctica began to build glaciers. Our good scientists do detective work and tell us how geology added to cooling the Antarctica enough to start building the glacier some 34 million years ago, and Greenland some 7 million years ago, when maybe the Isthmus of Panama, remember, it was wide open and fish were swimming from the Atlantic into the Pacific. It closed and it changed the circulation and so on and so forth, right? In some places the ice is 3 kilometers thick. There are entire mountain ranges buried beneath these thick glaciers. Every year the layer of excuse me, I got a frog in my throat. Every year the layers of ice becomes a bit thinner with climate change. In summer more ice melts away than is added during the winter. This is of course because the temperature is rising. But there are all kinds of things that speed up the melting process. They have strange names like Moulins and Cryoconite. Here is a cryoconite that we are looking at. Moulin is the French word for mill. I need to drink some water, and I forgot to bring water to my desk here. Moulins or mill are big round holes in the ice as seen here, and the water flows into them and away, swirling around like a whirlpool. This takes the meltwater to the underside of the ice. Excuse me. Which makes the ice melt faster and break up into pieces. That's how Moulins speed up the melting of the glacier. So if the water flows all the way to the bottom of the glacier where it's sitting on the rock, let's say, the water begins to act like a lubricant which makes the machine move smoother, so it makes the glacier slide on the rock, and that's not good news because it'll slide down the slope into the ocean. Okay, so the Moulin can make the ice melt faster and break up into pieces in this process. That's how Moulins speed up the melting of the glacier. And you also learned something else. If glacier melts and the water pond forms, the water pond has much lower albedo than the glacier, hence it begins to absorb more and more of the sunlight, and it begins to warm up more and more. Glacier melts and the melt pond gets bigger and deeper, and it begins to chew into the glacier, and that's how it begins to form a hole, and the hole can go all the way to the bottom of the glacier, as we'll see in a picture very soon. On the other hand, the Cryoconite is the black stuff that you sometimes see in the photographs of glaciers, a thin layer making all the beautiful snow look a bit grimy. The layer is made up of dust from the deserts and from volcanoes, and the soot, the black carbon from factories and cars. It's carried to the poles by the winds, of course. The black areas absorb more heat than the white snow because albedo is again being lowered by the dust and the dirt and the grime. This makes it melt faster and creates black holes in the ice as well. So you can see the cryoconite here. So that's another melting accelerator. Dirty snow melts faster, and with global warming and with climate change and with increased emissions come more pollution. Unfortunately, the recording got suddenly interrupted, so I'm continuing on. Experts would go and edit the gaps out, but I'm not going to do that because it takes time and you don't mind it being a little interrupted in the middle, right? So we were reading about the Moulins and the Cryoconite and the dirty snow and the albedo and so on. The North Pole's largest area of ice is Greenland. We keep saying ice, but remember to separate sea ice from glaciers on land. You are now smart enough to do that. But the other countries around the Arctic Ocean are also partly covered with glaciers. Norway and the US, parts of Alaska and so on. The sea ice itself is frozen for much of the year. There's a pack of ice as far as you can see, like ice floes, all frozen together. You've probably seen it in those photographs of the lonely polar bears wandering around and thinning sea ice and not having, food easily available, so they have to sometimes swim for hours and hours in the water, and they are not really meant to do that. Every summer some of the ice melts and every winter it grows back, but because the summers and winters are becoming warmer, more and more ice is melting away and less is growing back. Whatever remains in the summer frozen still has high albedo, so it makes it easier to grow back in the fall and winter. But if it melts away, then you have lower albedo and warming waters, and it's harder to freeze when the fall and winters come. Okay, so that's always bad news. Some predictions in fact say that the summer ice will disappear within a few years, hopefully not in your lifetime, but unfortunately you already know that the ice albedo feedback is making the Arctic warm faster. We called it the Arctic amplification and the polar amplification. The North Pole region is unlucky. It's warming up much faster than other areas on Earth because of the Arctic amplification. For centuries the sea ice worked as a protective layer against the heat, covering the ocean and insulating it with its white color. The ice reflected the sunlight. Now that the ice is disappearing, the dark sea absorbs far more heat. The heat that was stored under the sea is being released. It's not very warm, of course, because it's still in the Arctic and still very, very cold, but it's unfrozen, so it's still warmer than the layer of ice above. So you can see the North Pole with Greenland and some land glaciers here and sea ice here, and you see how Antarctica is different with land in the middle at the North Pole. Here North Pole is in the ocean, and the land of course can grow lots of glaciers kilometers thick, and it has sea ice or flowing glacier onto the ocean, and it is surrounded by the ocean. Makes for some very different behaviors here versus here. It is surrounded here and it's much fresher than the oceans here outside, let's say, and almost like a lake sometimes, and can freeze like a lake as well, but now it's freezing less and less. The South Pole region is the opposite of the North Pole in almost every way. When it's summer at one pole, it's winter at the other pole. There are no polar bears here, and there are no penguins here. So the South Pole has penguins and the North Pole has polar bears. South Pole is land surrounded by the sea here, the Southern Ocean, and North Pole is sea surrounded by land. Antarctica would fit into the Arctic Ocean almost like a cork. Ice on land can grow a lot thicker, so there is 10 times as much ice at the South Pole as the North Pole. Together, the two poles contain more than 99% of all ice on Earth. Even most of the fresh water is locked up in these glaciers. You think there is a lot of water on land with rivers and lakes and wells and so on, but actually most of the water is frozen up. South Pole is also much colder than the North Pole. That's because it's such a large landmass. There is much less sea to ease the cold a little. which means the ocean, if it is unfrozen, it remains warm. Right here you are surrounded and the entire ocean can freeze up. Okay, if you have it's also pretty mountainous. Antarctica, it's covered in glaciers, but it's actually lots of mountains underneath. If you ever been to the mountains, you will know it's a lot colder up there than in the valleys. The thick layer of ice in Antarctica makes the continent even higher and therefore even colder, because the glacier builds up several kilometers thick. Then the atmosphere is colder on top of the glacier on average. It's just as cold there in the summer as it is at the North Pole in the winter. The winter here is only as cold as the summer here, which means the winter here is miserably cold. How cold is it? On average, it's just as cold there in the summer as on average at the South Pole. The summer is as cold as the winter in the North Pole, around 25 degrees below zero in the summer. In the winter, it can get down to minus 60 degrees, which is colder than Mars. Mars, we say, is minus 50 degrees. This also makes a difference to the freezing ice. If the ice is going to melt on Antarctica, it has to get much warmer. You do see a large and small ice sheets breaking off around the edge of the continent here. That makes it easier for the glacier behind them to slide into the ocean. The glacier is sloping down, flowing down the slope onto the ocean, and the glacier is floating on the ocean. It's called shelf ice. It's getting moved up and down by the tides and the waves, but the ocean below is getting warmer and melting. The glacier from below can break it off, and when it breaks it off, the glacier on land can begin to slide, because the shelf ice would have anchored it over there. Right? If you don't understand, do not worry about it. Okay, that makes it easier for the glacier behind them to slide into the sea. These glaciers make the sea levels rise, of course, because they have come off the land. Remember, we build glaciers by compressing snow, and the snow is coming from evaporated ocean water, so we are constantly locking up the ocean water into the glacier, so the sea level keeps dropping. And the glacier melts, all that water comes back and the sea level rises. Melting land ice makes the sea level rise, then the water adds to the sea. Melting sea ice, though, makes no difference to the water level. Ice flows and sheets of ice on the ocean are already floating on the water. Why don't you see for yourself what happens when they melt? You can take a glass of water or orange juice and put some ice cubes into it that you can get from your father or mother or brother or sister that's old enough to go to the refrigerator and get you some ice cube. If it melts, you're not going to overflow the glass, it's just going to remain the same, right? So here is a nice picture of a Moulin, a poor scientist standing there, depressed, looking at what's happening. A scientist peers into a large Moulin that cuts through the western Greenland ice sheet about 30 kilometers north of Jakobshavn. Isbrae is the name of this place. Scientists can now get a sense of the geometry of these shafts by analyzing seismic signals created by waters plunging from the surface to the glacier base. Of course, seismic signals are what we measure during the earthquakes. So much water is falling that it creates a signal in seismometers sitting far away or taken by these scientists here. And you can see here, of course, the water is nice and blue, looks beautiful like a waterfall, but its albedo is much lower than the nice white glacier, which means it's going to absorb more of the sunlight. It's going to get warmer and melt more, and then you have the dirty glacier here, lots of dirt and grime and so on coming from pollution, etc., which is going to melt it faster as well because its albedo is much lower. It looks dark here, ugly dark, compared to the nice white clean glacier here. You can see in the background that maybe there is some more dirt there. So this is all adding up to melting the glaciers faster and faster. which adds to the ice albedo feedback and the warming and the Arctic amplification and the polar amplification and so on. So let's leave it here, come back and talk about the weird properties of water, which are also critical. Water, remember, is a very critical component of the entire business, because we are evaporating it, taking energy from the ocean and condensing in the atmosphere and releasing energy and creating winds and snow and glaciers and rain and so on and so forth. So we'll come back and talk about that. Okay.